floating point stuff. And we're going to do the arithmetic with it today, which is to say, last time we just encoded and decoded numbers, and that was it. But what about if we want to like add them, for example? Then things get a little bit more dicey. So to maybe motivate the idea of what we're going to do, let's just forget about floating point in binary and just do like uh, addition of numbers, normal base 10 way. All right, so in order to do that, I need a couple of numbers to work with, and let's just work with this, and I'm just making these up, okay? The 6.02, obviously I was a little inspired by that one, and actually let's do 6.022 just for giggles. Okay, can I just directly add these? I mean, if I had a calculator or something, yeah, maybe, but can I just say, oh, well, 6 plus 7 is 13, and so on and so forth. So why can't I just do that? Yeah, the exponents don't match, okay? So I can't directly add them because one of them is times 10 to the 23rd, and the other one is times 10 to the 21st. Now, if by coincidence they had the same exponent, I could just do that, but they don't. So I would like for them to have the same exponent so that I can just do the addition. They don't as of right now, okay, which means what I need to do is change one of their exponents. Okay, so that gives us two choices here, right? Which exponent do I want to change? The 23 down to a 21 or the 21 up to a 23? Okay, so why would you choose to do the 23 down to a 21? Okay, but wouldn't that be the same as doing the 21 up to 23? It just moved the decimal point the opposite direction? Yeah, okay. So from that standpoint, is there any reason to choose one of them versus the other? No. Huh? Um, well, we won't need a negative exponent here. Oh, okay. So yes, okay, if I shift the exponent by one, so for example, let's say I write 7.5, well, not 7.51, I make this 10 to the 22nd, then I have to write this instead, right? So increasing the exponent corresponds with shifting the decimal point left by one position so that like those two numbers you guys agree are the same thing. Yeah? Okay. Let me do one more. Also the same number, right? I could have made, for example, this one like that, right? So decreasing the exponent, I compensate by shifting the decimal point to the right and opposite on the other number. Okay. So which of the two would I rather work with? The 602.2 times 10 to the 21st or the 0.0751 times 10 to the 23rd? Mathematically, there is no reason to choose one over the other if all we're concerned about is math. Okay. But are we concerned just about math? No. What else are we concerned about? Hmm? I didn't hear what you said. Sorry. It was apparently funny. No. Well, okay. We're also concerned about precision. Okay. And so what I mean here is mathematically, I can write down as many digits as I want. Who cares? Right? Computer wise, though, I can't just write down as many digits as I want. There's sort of a fixed number that we're allowed to use. Okay. So let's take 6.02 times 10 to the 23rd. Okay. Let's say I'm going to let you write down 2 digits, exactly 2 digits. Would you rather write down 6.0 or 0.02? Why would you rather write down 6.0? Right, which is closer to 6.02? 6.0 or 0.02? 6.0, right? So if you're going to lose precision, would you rather lose it in small decimal places or big decimal places? The smaller ones, right? That's better. In like if you're going to be imprecise, you want to minimize that imprecision. Okay, so this would be sort of like um, the following. Well, no, that's we'll just leave it there. Okay, so accordingly, I want to like if I'm forced to lose precision, I'd rather lose precision with the smaller stuff than the bigger stuff. Looking at our two original numbers, which one is dealing with smaller significant values and which one's dealing with the bigger significant values? The 7.51 is least or most significant? Least because it has the smaller exponent. Okay, so um, when we change the exponent of one of the numbers to match the other, the choice we'll make is to always change the number that has the smaller exponent because that will result in the least loss of precision when all's said and done. Okay, so that means that I want to work with those two, 6.022 and the 0.0751 times 10 to the 23rd. Okay, so is that okay? And to recap, mathematically, there's no reason to pick one over the other, but we're not just doing math here. Okay, so it'd be kind of like, how many of you guys are taking some sort of science class this semester? Chem, physics, bio, right? What is it you guys have to worry about, particularly in physics, but really in any of the science classes when it comes to doing measurements? Yeah, there's significant figures which are a reflection of uncertainty. Every time you take a measurement with any kind of device, there's inherent uncertainty in that measurement, right? If you weigh something and your scale is only accurate to a tenth of a gram, well, that's probably good enough for most of the experiments you guys do. But if you're trying to, like, I don't know, make pharmaceuticals or something, you need to be a bit more precise than that. Okay, so, right. Now that I have the exponents that match, what can I do? I can add them, and what I'm really doing there is saying the following. Right? If their exponents match, then I can factor the times 10 to the 20 whatever out of each term and then just add the what's left. Okay. And so in this case, what happens if I add those? I get 6 point what? 0951. Did I mess anything up? Or no, 0971. Yeah. Okay. And there's our answer. Okay. So the when we took the number that had the smaller exponent and we deliberately changed it so that it violated our rule about having exactly one digit before the decimal point, what we were doing was denormalizing that number. Okay? Normal is it adheres to our rule, denormal is that it doesn't. So we deliberately denormalize so that we can add the easy way, and then we just have to write down, whatever the sum of the two mantissa parts is. Okay. The binary stuff is going to work exactly the same way. Okay. We have to change one of the exponents. The only other consideration we have to worry about is, so the two numbers that I added together here, how many digits did each of them have? The first one I had, 4? And the second one I originally had 3 or maybe 4 after I kind of messed with it. How many digits do I need to kind of mathematically write down the answer? 5, right? 6.0971. Let's say that I had told you you only can have 4 digits. What would have happened to the 1? It would have chopped off and been gone. Okay, we would have lost precision in that computation. Okay, now that didn't happen here, partly because we're kind of in math mode right now, where write down as many digits as you want. But in the binary stuff, where we have specified how many mantissa bits do you get? Exactly 4, right? If you need more than that, tough cookies, you don't have them. Okay, so there could be a loss of precision. All right, so now let's do this same sort of idea, but with actual binary floating point numbers. Okay, and for that, we just need to make up a couple of numbers to use as our example. Any suggestions? Give me a number. Okay, let me just use 4. Okay, and the reason is because with 4, you can't get any better than, I think, 4.25 or 4.75. So let me just use 4. But really, I'm going to think of it as 4.0. Okay, how do I write this as an 8-bit number? Well, 4 is 100.0 times 2 to the 0. Yes? Does this follow our rule? No. And therefore, what do I need to do? How many times did I shift the exponent or the radix? Twice. So I need to shift the exponent by 2. Okay, so now that I've got it that way, what is my exponent? 2. What do I have to do to that? Add 3, and so I get 5. How do I write 5 using 3 bits? 101. Right. So the exponent looks like a 5, but it only counts as a 2 because of that annoying plus 3. Okay. And then what's our sign bit here? Because the number that we're dealing with is positive, so 0 sign bit. And then what's our mantissa in this case? Just the zeros. Okay. Why don't I have to actually write down the 1? It has to be a 1, right? So this was the difference between doing this in binary versus doing this in decimal, right? If our rule for scientific notation is exactly 1 digit must go to the left of the radix, in base 10, there are 9 such choices, right? 1 through 9. In binary, if it can't be a 0 and it has to be exactly one thing right before, then what does that force the thing before the radix to be? A 1. And so I don't actually have to encode it. This gets me 5 bits for the price of 4, essentially. Okay, which is kind of nice. Okay, so there's our number. There's 4.0. Okay? All right, I need a second number because I want to add something to 4. So give me another number. 11. Okay? 11 it is. And I'm going to write 11.0. And let me actually put here a subscript of 10 because I mean here 11, not 3. Okay, just so we're clear that which base I'm writing in. Okay, so great. How am I going to write 11 in binary style scientific notation? Well, I have to do an 8, no 4s, a 2, and a 1. Okay, is that 11? 8 plus 2 is 10, plus 1 is 11. Okay, good. But what's the problem with that? Yeah, it violates our rules, so what do I need to do? Yeah, move the radix, and so I'll have 1.1010 times 2 to the, how many positions did I move it? 3, so I've got this. Yes, sorry. So it's 0110. There we go. Okay, so sign bit is what? 0. Exponent is what? 6, which I'll encode like this, a 4 and a 2, right? Okay, so why 6 again? Got to add 3 to it because of that offset. Okay, and then finally, what's my mantissa? 0010. Oh, 1, sorry. 2 1s, not, there we go. Okay, so there's my 2 numbers. Perfectly good. Okay? So, what I'd like to do is add these together. Now, what do we expect that the answer should be? I would hope I get 15, yes? Because last time I checked, that's what 4 plus 11 is. So let's see what we get if we go through essentially the same process that we did at the beginning with the 2 scientific notation numbers. We got to denormalize one of them, do the addition, and then possibly fix the answer at the end. And I'll show you what I mean when I say that. Okay. Okay. So are we good? Yeah. All right. So let's take. I'm going to need some more space. So let me just kind of copy and paste all of this onto the next sheet. Copy. Okay, so got everything we had before, and we want to add these. Okay, so what I'm doing, right, is I'm adding 1.0000 times 2 to the second plus 1.0110 times 2 to the third. That's the worst looking tree I've ever written in my life. Okay, so that's what we want to do, yes? All right, like in the example we started out in the beginning, in order to add these, I need to have their exponents matching, right? Which of the 2 am I going to mess with? The first one or the second one? In this case, the first one because he has the smaller exponent, okay? So I'm going to instead write this as 0.1 times 2 to the third. Okay, now the exponents match. Okay, Gucci? Yeah? All right. Now that the exponents match, I can do the addition. So I'll have 0.10000 plus 1.0110 whole thing times 2 cubed. Okay, perform the addition inside the parentheses. What do I get? I get that. Yes? Okay, so the answer is, what is our sign bit? 0, because it's still a positive number, right? What's our exponent? 3, which counts as 6, so what do I need to write down here? 110, that's 6. And then my mantissa is now what? 1110. Okay, because remember, it's the stuff to the right of the radix. Does this, in fact, represent 15? Well, if I shifted the the stuff, I would get this. Is that 15? Do I have a 4, or sorry, I've got a 1, a 2, a 4, and an 8, and that all adds up to 15. Okay, so this one worked. Everything worked great. We did, in fact, get 15 as the answer. That's a good thing. I think you guys would agree. Okay. Okay, so the bit that I mentioned about having to possibly fix the resulting number, this didn't happen here, but what about when we did that addition if we had some carrying going on? Okay, then it might have been the case that our sum actually violated the rule, in which case you just have to renormalize it. That didn't happen here, fortunately, but it could theoretically. Okay, so does that make sense? Yeah. Okay, so the TLDR here, right, is in order to add two of these things together, denormalize the one that has the smaller exponent, do the addition the way addition just works, and if necessary, renormalize the answer. Okay, we didn't have to renormalize anything here, so that was no big deal. This, by the way, let's look at the two, go back to the encoding for the two numbers I started with. 101, or sorry, the 4, which is the top one, and the 11, which is the bottom one. So I think I mentioned Friday, right, that there's this annoying +3 with our exponent, and at that point it was just shut up and do it. Why is it there? Okay, the reason that it's there is just looking at those two numbers, which one has the bigger exponent? 101 or 110? Which one's bigger? Who votes for the first one's bigger? Who votes for the second one's bigger? Yeah, okay. So it makes it very obvious which one of these two things is bigger. All right, now, how did we encode negative numbers when we were doing this with integers? We had to do the 2's complement stuff, right? So a 2's complement, in 2's complement, the very far left bit of all negative numbers is a 1. So if I wrote down 101 versus 110, I might look at these and think that actually they both represent negatives. They don't. Okay, so the exponent is not done according to 2's complement. It's done using this sort of bias offset scheme because it makes the process of determining which exponent is larger an instantaneous process. Okay, much easier. And why that's a good thing would be, well, let's think back to it for a moment to our circuit construction stuff. Doing even something simple like a NAND gate or an AND gate, or as you guys will see later this week once I finish the schematic and post it, the Xor gate, gets kind of complicated, right? So how would I build a circuit that could actually do floating point calculations? I would need a crap ton of gates. And so anything I can do to kind of simplify parts of the problem, make my life easier. Okay, and that's essentially the story behind the exponent. Why of that there's that off by 3 shift. Okay, it makes circuit stuff in terms of actually building a device to do floating point just easier. Okay, right. Okay, so question, preguntas, fragen so far. Then I'm going to blow y'all's minds again. No? Yes. For our answer? Uh, no, it's 2 to the power of 3. Ah, okay, good question. It can't be. So the question is, what would happen if the exponent was a 5, right? Could I write down a number that had an exponent of a 5? Sure, right? For example, well, let's just take powers of 2. 2, 4, 8, 16, 32. Okay, so let me take the number 32. I would write that as 2 times, or sorry, 1.0000 times 2 to the 5th. If I add 3 to that, what do I get? Okay, but my exponent can be how many bits? Only 3. How many bits do I need to express 8? 4. So what that means is that the number 32 is not expressible as an 8-bit floating point number. You cannot do it. Does that seem like a bad thing? Yeah? Well, okay. 32, right? Not all that huge of a number, okay? But we're also only using 8 bits. Should we really expect that we could encode everything with only 8 bits? No, like there has to be some sort of limit to how much we can actually write down. And with 8 bits, it's a pretty like small range of numbers. 32 is outside that range. Now, if I jump up to say doing 16 bits, then yeah, I could write down 32 no problem. Okay, but there's a limit to the precision and the size of things that you could do. Now let's all think about that from another perspective. Okay, um, I've got 8 bits to work with, yes, because we're doing an 8-bit scheme. How many different patterns are there that involve 8 bits? 2 to the power of 8, which is 256. Okay, so with this 8-bit scheme, I can write down 256 unique patterns. We've already said that one of the bits is a signed bit, so really I can do 127 positive numbers, right? The 128th would be 0. Well, if I can't do 32, but I can do 4 and 11, and we did like, I think 2.5 last time, right? Things like that. So there's some range of numbers, and I can only pick 256 numbers out of that range. Well, let's, I don't know, let me use my meter stick here or the inches actually. For once, inches is actually a good thing, right? How many markings are on this stick? Okay, so let's just say it goes out to, let's just say it's 3 feet, a yardstick. Okay, so that's 36 inches, and this thing is subdivided into halves, quarters, into eighths. Okay, 36 inches. How many markings per inch? 8. So how many total markings is that? What's 36 times 8? Well, 30 times 8 is 240, right? Plus 6 times 8 is 48. 288? Yeah? All right, is that bigger than 256? Yeah. So, floating point with 8 bits would be incapable of doing this many number of things. And would you guys agree that in 36 inches, and dividing into eighths, that's not all that precise? No? Okay, so what's the lesson here? Don't actually do this with 8 bits. If you want working precision, use at least 16, good God, right? And preferably 32 or 64. Okay, anyway, so let me get more to the point here. The thing that's sort of weird about floating point is, so let's say I've got 256 things I can encode, right? Would it make sense to sort of evenly distribute them across the entire range? Would that be logical? Maybe, maybe not. Turns out they're not uniformly distributed across the range, okay? And let me show you why. 3.125, perfectly good number, right? Let's encode that, okay? So what's step one? In fact, actually, let's take a pause. Let's see if you guys can come up with it on your own. Do we agree that this is what we got? So first off, it's 11.001 times 2 to the 0, right? Then normalize it. So what's my exponent? 1, which counts as 4, because I have to add 3 to it. 4 and 3 bits is 100, and there's my mantissa. Okay, you guys agree? All right. For your second task, encode 0.125. Okay, now I should hold up my Admiral Akbar picture, right? You guys know from Star Wars, it's a trap. Okay, so just fair warning, it's a trap. And the fact that it's a trap is interesting, and we'll discuss in a moment. Okay, and this is where y'all's minds are going to get blown. Well, first off, do you guys agree with my scientific notation style writing of it? Okay, so if we'll take that as given, right? My exponent's minus 3. What do I have to do to that? Add 3. What's that? Okay, so what's my sign bit? 0. Fine. What are my exponent bits? What is my mantissa? Okay. Does this bother anybody? Does it bother you? Or you're like, oh, that's cool. Why does it bother you? Well, so who said anything about 0? You're seeing a lot of zeros there, aren't you? Right? So what the problem is, if I handed you a bit pattern of all zeros and asked you, what do you think this represents? Instinctively, you would probably say 0, yes? That was certainly true in integer land. All zeros meant 0. So we got a problem. Would it be a good thing to be able to represent 0? Yeah? Well, if anything ought to represent 0, wouldn't this be the logical choice? All zeros? But according to what we just did, it also ought to represent 0.125. Well, it can't represent both, right? That don't fly. So, which do you think all zeros represents? 0 or 0.125? Which one should we choose? Well, okay. This it can't be both. We cannot choose both. Okay, you would rather be able to encode 0.125 than you would be able to encode 0. Okay. Well, I'm afraid you get to be my my whipping boy for the day, right? Um, you guys, no? Okay. Well, put on a beta hat, and then you can be the recipient, the scapegoat today. Yeah. Um, how many of you guys have seen the Indiana Jones movies, and in particular, The Quest for the Holy Grail? Right. Okay. So they get there. He goes through all the trials. The Nazi dude follows him. They get to the end. They run into the Knight Templar. There's a whole bunch of different cups over on a shelf, basically. And then there's the fountain of holy water. And the Nazi dude goes and he picks one and he fills it up with holy water and then drinks it. And then what happens? He dies, right? And what does the Knight Templar say to Indy after this? He chose poorly, right? Sorry, you chose poorly. Okay, we would rather be able to encode 0. Okay, which is choosing wisely, which is what Indy did. Yes. Okay, how many of you guys have not seen that movie? How many of you watched Monty Python over the weekend? Mm-hmm. Well, how many of you that hadn't seen it before watched it over the weekend? I see how it is. I'm going to start dislocating some shoulders if you guys don't take my movie recommendation seriously. Okay. Um, okay. So we would rather be able to encode 0. So this is one of the things about floating point that's a little weird is that the precision is not uniformly distributed. I can encode 3.125, but not 0.125. Is that kind of weird? Yes. Well, it's okay. As Boris Johnson said, them's the breaks. Well, it wasn't originally Boris Johnson, but yeah. No. You guys know who Boris Johnson is, right? Okay, just making sure. But yeah, them's the breaks. Okay, so this encoding of all zeros is an exception to our rules because it looks like it ought to represent this 0.125 number, but it can't represent zero also, and we need to have zero. Okay, so there are a few exceptions to the floating point encoding scheme, and some of the other ones, for example, let's say I have a bit pattern of all ones, that actually represents not a number. Okay, so what does not a number mean? What is that concept? Well, what happens if you like divide something by zero? Yeah, it's undefined, or the answer is not a number. Okay, or you do other operations like what other things cause issues? Arithmetic things that you're not allowed to do besides division by zero. Yeah, square rooting of negatives. Okay, what else? What about the logarithm of a non-positive number? That's an issue. Okay, and for the sake of discussion, we'll exclude the idea of complex numbers, right? Because what's the square root of a negative if you're dealing with complex numbers? Yeah, something I. Okay, well that's fine, but like you've somehow changed categories of numbers when you did that. Okay, so having the ability to encode the idea of hey, there's a problem with the answer, there's a problem with this computation is a good thing, right? You've all got cell phones, right? Put in like do a division by zero operation. What does it say? Okay, error, right? Or I mean, your graphing calculators may say something slightly different. But point being, right? Can you divide by zero mathematically? No. And so the calculator or computer, in the case of your phone, I mean, they're the same thing in that sense, right? Um, needs to have a way to encode that, hey, bro, something weird just happened. You just divided by zero. Okay. Yeah. Okay. So good. All right. Let me show you guys one quick thing. So I'm going to switch back over to the Mac, and I need to have Safari window open. So let's go to our dear Canvas page for un minute. So I posted something. I posted some floating point notes that I've been writing. And actually, when I looked back at them, the last time I had edited these was February 22nd, 2020. Some interesting things happened a few weeks after that. You guys maybe remember. Okay, so the let's see, where are the exceptions? I thought I put those in here. Okay, so there are exceptions, excuse me, and special encodings. Okay, and the exceptions allow us to encode. Well, okay, we just saw the zero issue, right? It's all zeros. But what about if I make the sign bit a 1? Well, then I have negative 0. And you say, well, wait a minute, Dr. McKinney, why negative 0? What the hell is negative 0? Like, does that make sense? Yes and no. But how many of you guys are in calculus? One-sided limits sure make sense, don't they? Wouldn't it be, well, uh, actually, one-sided limits are easier than two-sided limits, but it kind of allows us a way to kind of get at a sort of sidedness of the limits, in a sense. We've got encodings for plus and minus infinity and for not a number, which is a little different than infinity. So it may be a good way to put this. Yeah, would be log of 0 is minus infinity, but log of negative 1 is not a number. right? So it's sort of a different kind of uh, thing. Um, yeah. So now, how do I know that these exceptions exist, right? If we wanted to really understand all the gritty details for IEEE 754, what should we do? I mean, I know as men, we are genetically predisposed to doing the following, or predisposed against doing the following, right? But what about if I went to the IEEE and actually downloaded a copy of the standard? Right. So, like for example, let me go back to the standard for radix independent floating point arithmetic. Oh, that's 854. My bad. I wanted the 754. You know, I thought I had a copy of this dang thing. Um, Here it is. Good old internet. We can just steal it from France. Okay, so, well, here's the standard. And what does this mean we have to go through and do? Well, all right, there's a bunch of crap at the beginning and stuff. And then the table of contents. And how many pages is this? 60 pages, right? So, what are we as men genetically predisposed against doing? Reading manuals, right? You get your piece of furniture from the store, from IKEA or whatever. What's the first thing you throw away? The manual. Then you throw away the packaging that it came in, right? So, no, sometimes you just have to RTFM, read the manual, okay? So, the manual here, right, um, in IEEE 754 defines three binary formats, 32, 64-bit, and 128-bit stuff. Okay, so where's the 16 and the 8? They're not actually defined in the standard. So when I did the 8-bit stuff, basically I took the 32-bit idea and said, okay, if it had defined the 8-bit standard, what would it have looked like? And that's what I've given you guys. What's really fundamentally the difference between 32-bit and 8-bit? The idea is the same. 32 bits is just a lot more crap to write down. That's why I've kept it at 8 bits, just for convenience. Okay. Um, okay. So here are the some of the example or exceptions, and so I went through this and figured out, okay, what are the exceptions going to look like in the 8-bit format to sort of mimic what's in the real 32-bit format. Okay. Okay. So Gucci. All right. So, two other things for this week. We got some new stuff to talk about on Wednesday, and then Friday we're going to do kind of two things. Um, Once I finish the schematic, I was almost done before class. For Friday, I'd like you guys to build the Xor Gate. Now, good news, you're already 1/3 done with it because you've all built an AND gate, yes? So on two other breadboards, build an AND gate and an OR gate, and then put them together, and bam, that gets you an AND gate. And we'll sort of show those off on Friday because also I think I mentioned the film crew is going to be here. So don't look like a complete slob on Friday. Um, I mean, I know that's easier said than done, given that it's homecoming week and a bunch of you are freshmen, right? And you're going to be up all night. Oh, no, wait, you don't have to guard the bell this week. So are you still going to be up all night anyway? Practicing chapel sing or whatever kids these days. So anyway, so pay attention to Canvas, and I will see you guys on Wednesday, if not sooner.